Okay, so today we will start with fixed point methods, and I'll try to motivate why this theorem or definition here is so important. So this is what we did at the end of last lecture, so I thought I was going to repeat it. So, if you're given a sequence of these vectors, I gave an example in the last lecture of a sequence like this. If you're given this sequence of vectors in this n-dimensional real space, they will converge towards some given x with the norm, well, just the norm defined as this. If for a given epsilon that is positive but small, there exists a number dependent on this epsilon such that the norm or the length between these two vectors is smaller than this epsilon for some kind of big number. In just real space, in one-dimensional space, it could be that you have some kind of function that is converging toward this here. Let's call this x without a vector. And then you have some kind of xn's, which go all the way down here, and they will converge toward this number here. It's basically the same concept. And we will start in one dimensions. So, fixed points. What is a fixed point? Definition. F. Fixed point for a function g of x function g of x, the real number p, so p in R, such that function of itself, so p of p is the number itself, like so. This is in one dimension. In n-dimensional space, it's pretty much the same, just with different notation. So here we are given some kind of matrix or some kind of transfer, some kind of function t goes from real n-dimensional space to real n-dimensional space, and x of n t. No, of course not. N. So if you're given this, so this is something that sends something in n-dimensional real space into the same n-dimensional real space. Given by this matrix or this function t applied on the vector x, such that you get the vector out by itself. Okay, and then we'll talk about a result we can use. So how can we find these fixed points? Well, if you have a function with a so-called contractive fixed point, then you can just input whatever in the function, and you will find, in the end, find the fixed point. I'll show an example of this. So I'm going to call this a result, and should be motivated in the book. Fine. So we're given a function, this g of x, and we want to check if it does have a fixed point. So we're given a function. Yes? This here? Oh, I can't just wait. Let's try again. So we are given function g of x. Okay, so this is what we want to look for fixed point for. And then we are going to assume that the derivative exists on an interval and g of assume that the derivative of this is defined for interval AB. And that the absolute value of the derivative of this function is less than k. It's just a random number, but this number has to be less than 1. And then again, for all the x's inside this interval AB. Then g of x, the unique fixed point. This doesn't exclude other fixed points, but now it has a unique g of x. Unique fixed point inside this interval. Okay, how can we use this? So we can look at the derivative of the function. If this is less than 1 inside this interval, then it has a unique fixed point inside there. So an example of a function like this is g of x. So g of x equals x half plus 10. Okay, can anybody tell me what the fixed point of this is? Just by looking at it. So if I input 20 here, I should get 20 out. But we also see that the derivative of g of x, well, that's just going to be a half, which is less than 1, and it's going to be half on whichever interval you try. So it's from minus infinity to plus infinity. We can just try here, and we see that g of 20 equals divided by 2 plus 10, which is 20. So here we see that g of 20 gives us 20. So 20 is a fixed point here. So if you try this on your calculator and you just say, first you have to input a number, so you just press 1 on your calculator, and then you can press the n's divided by 2 plus 10, and then can just keep pressing equal. And this should converge to 20 in the end. But we aren't that concerned about one-dimensional functions. We want n-dimensional functions. So how does this look like in n dimensions? So we're going to assume if there exists, or if there's some kind of number alpha less than 1, know what this means? So there exists some kind of number alpha less than 1 such that the so-called norm between, or distance, e of applied to x minus b applied to some vector y is less than the norm of this number that's less than 1 times the distance between vectors for, well, for x and y in Rn, then this t has precisely one fixed point. And why is this important? Well, in engineering, we'll often get linear systems with many thousand variables, and you can express these in a D matrix, and you can then solve this, for instance, a partial differential equation by using these methods. So the first one we'll be looking at is Jacobi iteration. And I'm going to start off with an example. Yes? This is the norm of. So the norm of the distance between these. As we had in the last lecture, a norm can be many things, but it has certain properties. And this is general, so as long as you have defined a norm, this works. And you can have many different types of norms. You can even have norms on functional space. So for instance, an integral of two functions can in some sense be a norm also. I mean, you need to have defined a interval and a lot of other stuff, but yes, a norm is abstract. An inner product, that's a norm. So it's easier to just think about this norm as an inner product in those two. So now I'm going to try to use what we learned last lecture, or the end of last lecture. So we'll start with this, and I will try to improve it, something called Gauss-Seidel iteration. an example. I am given the system of equation for x minus y plus z equals 7 for x minus 8y plus z minus 21 minus 2x plus y plus 5z equals 15. So if you're familiar with if you're familiar with linear algebra, this can be written 4 minus 1, 1, 4 minus 8, 1, 2, and then yes, 1, 5. So that's just the coefficients on this left-hand side. And we're going to make an augmented matrix. We get 7, 1, and 15. And we can perform Gaussian elimination on this one, and we'll get an answer. But this is a very easy system of equations. Here we can actually do it. And bigger, you can't. So I'm just going to solve it here. So the solution to this system, either this or this, that's the same. That is x equals 2, y equals 4, z equals 3. That's the solution vector, the vector we're after when we're doing these Jacobi iterations. Okay, so what's the gist of these Jacobi thing? Well, we can rewrite this system of equations to actually express x as y and z, and y as z, and z as x and y. How will this look like? Well, x 7/4 plus 1/4 y minus 1/4 z. Okay, so that's, I've just rewritten this equation, basically, the first one. Second one, y equals, okay, I'm gonna have that in front, 21/8 plus half y, yes? Oh, yes. Minus 7 plus there. Wasn't it? No, that was correct. Because equation this. So you move this over there, divide by 4. A half x plus 1 z, and then the last one, z equals 3 plus 2/5 x minus 1/5 y. Okay, so now we basically have a new system of equations. But we can rewrite this as well. So now we have our Jacobi process defined. Looking at all the coefficients there, see that we want to iterate this. So we're looking for fixed points in all of these. So if we want to make this into an iterative process, we can basically just say that the next number, k plus 1, equals the 2 preceding here. I, k, 1, preceding xk and preceding x, and the next z expressed by the preceding x and y. Yeah? This is the same as regular fixed points, only that dimensions. In matrix form, well, we're gonna have this is a matrix now. So this x vector contains x, y, and z, or written more verbose, x1, no, yeah, k plus 1, y, k plus 1, and z 1. Sure. False. Now we can just use the coefficients here. So we have in the first one we have 0 x's. We have a fourth y case and minus fourth. So that's basic. And then we have 1/2 x. Okay. We have 0 y's and 1/8 previous zk. I'm gonna fill out this. Fifths minus fifths. 0. K, y, k, z, k, and then we have to add vectors 7 fourths, 21 eighths, and 3. Like so. So this is going to be our T matrix. Plus 1 is T. I will define how to actually make this in a more general manner later. Okay. Plus constant is this C here. So if you compare this with the sample function that had a fixed point, then you see, well, this is x divided by 2, basically. So E here is 1/2, and this C is just plus 10 in the example showed earlier. This is just with more dimensions. Okay, so can we actually try this? Really? See? So what am I trying to do here? Okay. This is the same matrix as defined here. So that's the T matrix. We have the C, that's the same as behind here. This is just a random starting vector. So I'm just gonna try 1, 2, 2. I mean, just whatever. And this is the true one. This is what we get when we try to solve this using Gaussian elimination. I'm running 15 iterations. This x here is the vector, so the x vector. Its dimension is 3 and plus 1. And this is just for printing purposes. Probably have taken away some indentation here. So this is basically just printing out something. So find all of those, and then print this. We see at so what I'm trying to do here is at iteration 0, xk is 1, yk is 2, and zk is 2, which is this vector here we're trying. So what happens if we try to put this into the system? that is what we're doing here. So if you just ignore this line 19 and 20, which is just printing the same line as here, and look kind of iffy. Then we just say that x of the vectors, so so this is the x vector, or so this is size 3, so for x, y, and z, and the next iterations, which is k plus 1, then we just want to solve this previous x, y, z, and and adding this c vector. And this should get us the fixed point. And it does. There you see, end up at something that's very close to the true vector. And if we just try more and more iterations, we will get closer and closer down to machine precision. And the norm I've chosen here is just Euclidean norm, which is the square root of the sum of the squared, the square root of the sum of the squared differences. Euclidean norm, the one you're used to, like for finding distances. We can try to have 150 iterations, and we will get even closer. So basically 0 error. With we are there. So this is kind of a toy example, but in for bigger matrices, for more variables, in some engineering problems, you can have thousands of variables. You don't want to do this with thousands of variables. That just takes too long. But we can actually improve this method also. I'll get to later, but just as a tease. Okay, so first, I try to estimate the next xk plus 1. Okay, why should I use, so xk plus 1 is going to be a better guess than xk, which I'm using here. So why can't I just put this number into here? And now when I'm calculating zk plus 1, I have two better numbers, which is xk plus 1, which is available to me, and y k plus 1 down here. That is Gauss Seidel. So that's the next topic we'll get to. But first, I'm going to try to formally explain the Jacobi iteration, not just with an example. Any questions or? Yeah. This thing? Would be. No. I just removed the equations. You might be correct. Yeah, I could have had some mistake there. But it did work though, so. Either the process is robust or I didn't do any errors. Who knows? But yes. Jacobi iteration. First, we're going to do it on component form. So basically just looking at each component in the versions. So first, we want to solve the ith equation in ax b for xi. And here xi, it can also be y, z, whatever. far but 4. How do we do this? Oh, we can this equation from j equals 1 n skipping itself not equal y. So that number, oh well, that index and that index shouldn't be the same. So I can't express x as a function of itself. I try to get everything on the, well, the x on the left-hand side and the rest of the variables on the right-hand side. That's basically what this means. A I j x j over I plus b I over a I for all of these 1, 2, and 1. So you can try to do this with example where n is 3. See if this gets you the same. Solution. So that's step 1. Where are we? Here? It is an A. Supposed to be an A. See? So these are the elements of the matrix A. Okay, so next we want to find the next iteration xi. Oops. So I'm going to write, I know that I wrote k plus 1 the subscript last time, but of space, so now it's be up there. It's not to the power of, it's the next one. Okay. Basically the same equation. J equals 1, j not equal I, so we skip this. From n, a, j, kth, a, I, plus bi divided by a, I. So it's basically the same, only we're looking at previous iteration. Okay, but how does this look like? So this is component form, because you're expressing with components in the matrix. Yeah. Yeah, to I. Yes. No, to yes, to I. Yes, to I. So, component form. This is what is being used in programs if you're using Jacobi solver. Most probably you won't use a Jacobi solver because there are better solutions. But in matrix form, you have to split up matrix equals, so D, this is the diagonal elements, L is the lower triangular, and U is the upper triangular. And I know some of you did this in exercise 0. So the diagonal part, and L, that's the strict lower triangular, and U is the strict upper triangular. Like so. Okay, so that's A. We're solving this AX equals B. A X to B, oops, B plus L plus U X equals B. Or the diagonal axis equals minus L plus U X B. And then we can invert this, and that's a diagonal matrix. I'll show a trick how to invert diagonal matrices. So equals minus the inverse L plus U X plus this. Oops. The inverse vector, like so. And then we simply get that this is our B matrix, and this is the B. So the problem here is inverting the diagonal matrix, but that's pretty easy. So give you some time to write. And we have that if D is D1, 1, D1, no, D2, D3, 3, rest is just zeros. Then the inverse, this matrix is basically the inverse of the elements D1, 1, 1 over D2, 2, and 1 over D. So you don't really have to do an inversion there. But it's a pretty straightforward way of solving it. So we should be able to do this in MATLAB. Hope. Either component form or in just matrix form, like this. And here you can actually use help functions to find the upper and lower triangular parts. I don't remember on the top of my head if MATLAB does the strict lower triangular and strict upper triangular, but it's easy to check. So strict means that, strict lower triangle means that you don't have the diagonal in it. So if you're using this 3U and 3L functions in MATLAB, try to check this first. But as I alluded to, you can actually improve this, which some clever guys figured out a couple of 100 years ago, I think. Gauss and Seidel. GS iteration. So it's similar as we did in the example. So I'm just gonna recap the equations as we had. Is x plus 1. Write them in a slightly different form. Yk minus zk divided by 4. This is basically the same we had earlier. Just instead of 7/4 and divided by 4. Or just, yeah. What you do then, we can actually use the answer. So this xk plus 1 in the next y, which is 21, 4, xk plus 1, zk, because we don't have that yet. 8. So you see I take, first I solve this one. I have an updated number. And I put it here. Then again, third one, 1, oops, 15 plus 1 minus y plus 1 divided by 5. So then we can use this one on here, on here. So the theory by here is that, well, why not just use this when you've already calculated it? And this is going to iterate quicker. And it actually looks better if you implement it correctly in MATLAB. It looks easier. So do you get why this is kind of a better way of doing it? No? Mm. You're kind of doing a half update for each of them. Kind of an intermediate step, an improvement of the Jacobian. Yes? The break? Last questions?